Hello college algebra students. So today we are going to take a look at how do we work with exponential and logarithmic equations. So we're going to deal with equations, right? So we're going to, which means you're going to have left hand side and the right hand side. Now how do we work with them? So let's take a look at how do we deal with the exponential equations and then logarithmic equations. So when you work with exponential equations, you have an exponential expression on the one side. On the other side, you might have a constant or you might have an exponential equation, right? If you have both sides of the equation, if both of them have bases, if both are exponents, right, exponential expressions, right, then see if the bases match, right? If the bases, if they match, right, then all you have to do is to use this particular formula right here. I'll show you in a minute how do we do that, and then set the exponents to equal to one another and then solve for x. If they don't match, then what do? You take the logarithm on both sides. You take the logarithm on both sides and then isolate the x and then you solve them, right? That's how you work with exponential functions. When you deal with the logarithmic functions, very similar. If both sides have the log terms, then you condense them, you condense the both sides and then cancel out the logarithm. In other words, taking exponents on both sides and then solve. If that is not the case, if only one side has the log, the other side does not have the log, then keep everything on the log one side, move everything else on the other side, and then condense the logarithmic term and then use the exponent form and then solve it, right? So that is the general idea. So again, so let me summarize it. When you deal with the exponential or logarithmic functions, if both sides, you have an equation, you're going to have a left hand side and the right hand side. If both sides have the log or the exponents, right, then then you just, if it's an exponential function, you take only the exponent and then set them equal to one another and then solve them. If it's a log, if both sides have the log, then you just take the inputs and then set them equal to one another and then solve them, right? That's what we are going to do. So let me show you how do we do that. But before I go, let me recollect a couple of formulas in here that might be useful for you. Some exponential formulas and logarithmic formulas that might be useful for you. If you recollect, we know that a to the m times a to the n equals a to the m times n, right? A to the m over a to the n equals a to the m minus n. A to the m raised to the n is equal to a to the m times n, and 1 over a to the n is equal to a to the minus n, and square root of a would be a to the 1/2, and cube root of a would be a to the 1/3. In general, the nth root of a equals a to the 1 over n, and someone asks you what is the 1 over square root of a, and that would be 1 over a to the 1/2, and this formula, using this formula right here, you would see that this would be a to the that's a 1/2, a to the negative 1/2, right? See, so these are some formulas that we are going to be using. So it's a good it's good to remind ourselves of these formulas. All right, let's use these formulas and then we solve them. So the property that we are going to use in this particular one for solving the exponential equations is this: if b to the m equals b to the n, in other words, if the bases are exactly the same, then m should be equal to n. As long as the bases are same in the exponential equation, then the exponents must be the same. So that's what we are going to use it to solve here. So now what I am going to do in this particular problem is the following. I have an exponential equation right here, right? And I don't have the same base. I have 5 here and I have 125 here. So my goal is to see, is there a way that I can convert one of them into another? I cannot convert 5 into 125. That's going to be more complicated, but I can definitely rewrite the 125 in terms of the powers of 5, and that would be 5 cubed, and this is 5 to the 3x minus 6. As you see here, now I have the same base. I have 5 here and I have a 5 there. Since I have the same base, these two should be equal, right? These two should be equal. This 3x minus 6 should be equal to 3, and that's what I am going to do. So now I'm going to set this equal to one another, the powers, 3x minus 6 equal to 3. Now I have an algebraic equation for x, right? I'm going to solve that. To do that, I'm going to move 6 on the other side. If I do that, that is going to be 3x equals 3 plus 6, which is 9. And so therefore, I have x equals 9 over 3, which is equal to 3. So therefore, the solution for this particular problem would be x equals 3, right? That's the solution for this particular problem right there. Let me use the same idea in solving the second problem. All right, now if you take a look at this problem right here, I have 8 to the x plus 2 equals 4 to the x minus 3. Now again, I don't have the same bases, right? I have different base. Now, is there a common factor between the 8 and 4? Yes, I found a common factor, and that common factor is 2. You all agree with me that 8 is equal to 2 cubed and 4 is equal to 2 squared. I'm going to use that. So I'm going to rewrite this left hand side as 2 cubed raised to the power of x plus 2, and the right hand side as 2 squared raised to the power of x minus 3. As I showed you earlier, as I told you earlier, here is the form that we know. A to the m raised to the n is equal to a to the m times n. I'm going to use that particular formula in here. If I do that, ladies and gentlemen, what I'm going to have is the following. So this would be 2 raised to the 3 times x plus 2, and that is equal to 2 raised to the 2 times x minus 3, right? Now I have the same basis. I have 2 and I have 2 here, right? I have the same base on both sides. So therefore, now all I'm going to do is to set the exponents equal to one another. When I do that, I'm going to have a new algebraic equation, which is 3 times x plus 2 equals 2 times x minus 3. Now let me try to work with this equation, right? Let me move these things on the other side, and also I'm going to shrink it. So now what I'm going to have here is the following. What I have is, if I distribute all this, if I distribute the 3 and if I distribute the 2 in here, I am going to have 3x plus 6 equals 2x minus 6, right? Now my goal is to solve for the x. So I am going to move the 2x on this side, 6 on the other side. When I do that, you would agree this is going to be 3x minus 2x. I'm grouping all the x terms, right? And then this is going to be minus 6, another minus 6. On my left hand side, I have x, and the right hand side, I have negative 12. And that is the answer for this particular problem right there. All right, and that's how we solve these ones, right? Now let's try to solve the example 1c. Now if you recollect, I told you earlier, I told you this formula right here, right? And this is the formula that we are going to use for this particular problem, right? Let me do that first. So what I have here is I have a 1 over root 2, which is 1 over 2 to the 1/2, which is 2 to the negative 1/2. So I'm going to take a look at my right hand side, and I'm going to rewrite it as 2 to the negative 1/2 as the first one, as a part of the simplification. So I have 8 to the x equals 2 to the negative 1/2, right? Now I have a nice exponential equation here. So let's see how do we solve that. Again, I don't have a same common base, and now I have to find a common base between them. I have 8 on one side and 2 on the other side. So how do I do that? And there is a common factor between the 8 and 2, and that is 2. Now you agree that I can write 8 as 2 cubed. So this is going to be 2 cubed to the x equals 2 to the negative 1/2. As I showed you earlier right here, I'm going to use the same thing. So therefore this would turn out to be 2 raised to the 3x, right, equals 2 to the negative 1/2. since now I have the common base, right? I have a 2 here and I have a 2 there, so therefore the exponents must be equal to one another. Exponents must be equal to one another. So now I am going to have a nice equation right there, and that is going to be 3x is equal to negative 1/2. Now I'm going to divide by 3 on both sides. When I divide by 3 on both sides, you would agree that I'm going to have x equals negative 1/2 divided by 3, which is negative 1/2 times 3, which is negative 1/6. And so therefore the answer or the solution to this particular problem is x equals negative 1/6. And that's how we solve these exponential equations. Alright, so here, so far in example 1a, b, and c, we worked with exponential equations that we were able to simplify to have the same basis, right? Because there was a common factor between the 8 and 4, there was a common factor between the 5 and 125, and there was a common factor between the 8 and 1/√2, right? Or basically 8 and 2, we were able to do that. So when you have the, so we were able to simplify into have a same base, and then we were able to solve them. Now let's take a look at the ones, how do we solve the exponential equations that does not have common basis, something like this, right? Something like this. So before I solve this problem, I will solve a simple one, then you should be able to follow this one. So let's take a look at this particular very simple logarithm exponential equation that does not have a common base. Suppose you have a problem of 3 to the 2x equals 5 squared, right? How do we solve them? We don't have a common base, so what we are going to do, alright, so let's see how do we solve 3 to the 2x equals 5 squared. And you see that 3 and 5 are two different bases, and there is no common factor, right? Mathematically speaking, these are called, the 3 and 5 are relatively prime, right? There is no common factor between them, so we call them, they are relatively prime. So therefore here we may not be able to use the same method that we did earlier. So then what do we do? In this case, what I call, remember this, Tennessee lobster. What do I mean by that? So I'm going to say TNLOBS, right? So what is this TNLOBS? That basically means taking logarithm on both sides, right? So I'm going to take, as a matter of fact, I'm going to take a natural logarithm, right? Taking natural logarithm on both sides, right? TNLOBS, right? So what I call Tennessee lobsters, right? That's what we're going to use. This is for you to remember. There's no such a thing as Tennessee lobsters in the math, right? So if you remember this Tennessee lobster, then we can kind of solve them. So I'm going to take natural logarithms on both sides. When I do that, then what's going to happen is that this is going to be ln of 3 to the 2x equals ln of 5 to the 2. And then we are going to use logarithmic formulas, right, that we learned in the previous section. So if I recollect some of them for you, right, let's recollect some of the formulas that we learned last time. Ln of x to the n equals n times ln of x, right? And then ln of e is equal to 1, and ln of e to the n would be equal to n. And if you want, logarithm of 10 is equal to 1, and logarithm of 1 is equal to 0, and ln of 1 is equal to 0. But most important thing that we're going to use right now is this particular formula right there. So when you have something in power, you can bring it down, right? So since I have something as a power here, and the power here, I'm going to bring them down. So if I bring them down, this is going to be 2x times ln of 3 equals 2 times ln of 5, right? Now my goal is to solve for the x, so therefore I'm going to keep x on one side, move everything else on the other side. To do that, I'm going to divide both sides by the ln of 3. When I do that, I am going to have 2x equals 2 times ln of 5 over ln of 3, right? I'm dividing both sides by ln of 3. and that tells me now again I don't have an x in here, right? So again I have to isolate my x. To do that, I'm going to divide both sides by 2. When I divide both sides by 2, I am going to have x equals 2 times ln of 5 over 2 times ln of 3, and I can cancel the 2 and 2, and I will be left with ln of 5 over ln of 3, and that's the solution for this particular problem right there. So again, let me quickly go through what I did, right? So when I find an exponential equation that does not have a common base, right? What I did was I did what I call taking natural logarithms on both sides, which I call Tennessee lobsters, right? TNLOBS, taking natural logarithms on both sides. And when we do that, then in this particular problem we use the this particular logarithmic exponential property, which is ln of x to the n, or ln of x to the a, whatever you want to call it, right? Equals n times ln of x, and that's what we used it. And then we pretty much now I have an algebraic equation, except that these are ln of 3 and ln of 5. But remember, these are constants, right? These are numbers, so they are constants. I can work with them as if they are numbers. So then we were able to divide and multiply, and then we were able to isolate x. That is the idea in solving them whenever you don't have common basis. All right, now let's take a look at this particular problem, which is 3 to the 2x minus 1 and 7 to the x plus 1. Here is also, I have 3 here and I have a 7 there, and these are not common bases, and unfortunately I don't have a factor where I don't have a common factor between the 3 and 7, and the 3 and 7 here are co-primes of one another. So therefore I can't do that. So here I have to use what I call, Tennessee lobsters idea. So what I'm going to do, I'm going to take the very first step as taking natural logarithms on both sides, right? If I do that, then this is going to be ln of 3 to the 2x minus 1 equals ln of 7 to the x plus 1. And by the way, you don't have to take the natural logarithms. You can take the regular usual logarithm of base 10, but we tend to prefer the natural logarithms for various reasons. I personally prefer the natural logarithm, but if you would like to go with the regular logarithm log base 10, that's perfectly all right as well. Right? All right, now let's see how do we solve that. So I'm going to use the same formula that I did over here. I'm going to use the same formula that I did over here, right? ln x to the n equals n times ln of x. So when I do that, you see that the power here is going to come down. The power here is also going to come down. So now I am going to have 2x minus 1 times ln of 3. Remember, ln of 3 is a constant, equals x plus 1 times, that's x plus 1 is a power, so it's going to come down, times the ln of 7. Remember, ln of 7 is also like a number, a constant. Now my next goal is to isolate the x's, right? To do that, what I am going to do, I am going to distribute all that. This is a little bit of work. I'm going to distribute all that and then I'm going to work with them. So if I do that, ladies and gentlemen, my left hand side is going to be, I'm going to multiply 2x with the ln of 3 and then negative 1 with the ln of 3. Then I'm going to multiply x with the ln of 7, then 1 with the ln of 7. When I do that, this is going to be 2x times ln of 3 minus ln of 3 equals x times ln of 7 plus 1 times ln of 7. Remember, ln of 7, ln of 3, they are all constants, so we are okay, right? There we can treat them as numbers. All right, now what do we do? I don't have enough spaces, so therefore I am going to kind of shrink them, if you don't mind. All right, so let's solve them. Now what I have is I have this particular equation right here, right? My next goal is to I group all the x terms, and I have one x term in here and I have another x term in here. So I'm going to keep these two together on this side. I'm going to move this on the other side. So when I do that, what's going to happen is the following. I am going to have 2x times ln of 3 minus x times the ln of 7 equals ln of 7 plus ln of 3. So what I did here is I moved this one on this side. So basically I subtracted x times ln of 7 on both sides. When I do that, this is going to go away on this side, and minus x times ln of x is ln of 7 is going to stay on this side, and that's what I have as my left hand side. Now I want to get rid of negative ln of 3, so I'm going to add ln of 3 on both sides. When I add ln of 3 on this side, this is going to go away, but then this side is going to have ln of 3, and that's what I have right there, right? In other words, I can move this side. Now the positive becomes negative, and I can move this the other side, the negative becomes positive. Another way to think about it. All right. So now again I am going to factor the x, and I'm going to keep everything else. If I factor the x, ladies and gentlemen, I have x right here and I have x right there. And if I take the x out, the very first term I will be left with 2 times the ln of 3. The second term I will be left with ln of 7, and that equals ln of 7 plus ln of 3, right? Now my goal is to isolate x, remember. So I'm going to divide both sides of the equation by this particular term right there. When I do that, then what happens is that my left hand side is going to be simply x, and the right hand side is going to be ln of 7 plus ln of 3, and the whole thing is divided by 2 times ln of 3 minus ln of 7, and that is your answer for this particular problem. And that is your answer for this particular problem, and that's how you solve these kind of problems in there. Of course, this is a little bit involved. This is a little bit extensive in terms of the computation, but if you work with them, you should be able to solve them. If you practice enough, you should be able to solve them easily. All right, let's do example 2b. Right, here is also we have a problem here where I have this is an exponential equation right here. What I have here is an exponential equation, right? But the thing is, one side is an exponent, the other side is not. So what do we do? Again, if you go back in here, as it says, right, if you don't have the same basis, right, we have to take the natural logarithm on both sides and so on. But before we have to take the natural logarithms, right, we have to take the log on both sides and then isolate the x and then solve. That is the idea. So now what we are going to do here, before I do that, this is a little bit complicated. For that reason, what I am going to do here is I am going to keep the exponent on one side and move everything else on the other side. To make my life easy. So for that, what I am going to do, I am going to move 5 on the other side. When I move 5 on the other side, what I am going to have is the following. So 7e to the 2x equals 58 plus 5. Right, and that tells me 7e to the 2x equals 63, and I'm going to simplify as much as I can, right? That's very important. If I simplify this as much as we can, I would have e to the 2x equals 63 over 7, which is equal to 9. So now I have the exponential equation, which is e to the 2x is equal to 9, right? Now we can solve that. Now how do we solve that? Again, we don't have the same base. This is e, this is 9. So I'm going to do my Tennessee lobsters. So I'm going to take natural logarithms on both sides, what I call Tennessee lobsters, of this equation, which is e to the 2x equals 9. When I do that, then I'm going to have ln of e to the 2x equals ln of 9. We are going to use the same thing that I mentioned earlier, right? This exponential rule, right here, which is if I do that, then this is going to come down. Then what I have is I have 2 times x times ln of e equals ln of 9. As I shared with you earlier, ln of e is equal to 1, which I'm going to use it right here. If I do that, then you see that this is going to be 1, right? So therefore this would be 2 times x times 1 equals ln of 9. That means 2x is equal to ln of 9. So to isolate the x, I am going to divide both sides by 2. If I divide both sides by 2, I am going to have 2x over 2 equals ln of 9 over 2, and 2 and 2 gets cancelled. So now I have x equals ln of 9 over 2, and that is your solution to this exponential equation, and that's how you solve this problem. All right, let's see how do we solve the next one. This is a little bit involved. We are going to do something called substitution method. I will show you in a moment what that is. All right, so how do we do this one? So here, if you recollect, e to the 2x is same as saying e to the x the whole squared, by the way, right? Because a to the m times n is equal to a to the m to the n, or you can also say that is same as saying a to the n to the m, right? So since this is e to the 2 times x, I can write this as e squared to the x. I can write this as the e squared to the x, or I can also say this is e to the x the whole squared. These are one and the same, and that's what we are going to use right here. And then we are going to convert this into a convert this equation into a quadratic equation, and then we are going to use and solve them, right? So what we are going to do, we are going to do some sort of substitution, and then convert using the substitution. We will convert this, we will transform this into a quadratic equation, and then we are going to solve the quadratic equation, and then we are going to do resubstitution back, and then we solve for the x's, right? Let's see how do we do that. So here, since I have e to the 2x and I have e to the x, so what I am going to do, I am going to do the substitution. I am going to say let u is equal to e to the x. Then as I shown you earlier here, then u squared, which is e to the x the whole squared, becomes e to the 2x, right? Because of this right here, and because of this property, right, that becomes u squared becomes e to the 2x. Now if I do that substitution back in here, if I do the substitution back in here, right, if I do the substitution whatever that I have right here to back in here, then this equation turns into the following, which is u squared minus 8 times u plus 7 equals 0, right? This is my u squared, this is my u squared as you see here, and this is my u as you see here, and that's all I did. I just simply plugged it in right here. Now this is a quadratic equation. We know how to solve them, so that we can factor this out. If I factor this out, you all would agree with me, this would be u minus 1 times u minus 7 equals 0. That's going to give us two solutions, and those two solutions are the following: u is equal to 1 and u is equal to 7. Now we are going to solve these two. To do that, what I am going to do, let's see what this means to be u equals 1. Let's solve this particular one. U is equal to 1, and what is u? U is equal to e to the x. If I resubstitute that back, so I have the equation now, e to the x is equal to 1. And how do we solve this exponential equation? So we are going to, as I said earlier, we are going to do, just like we did last time, we are going to use the Tennessee lobsters, which means taking natural logarithms on both sides. When I do that, this is going to be ln of e to the x is equal to ln of 1. If you recollect what I did earlier there, ln of, remember, ln of e is equal to 1, right? Ln of 1 is equal to 0, right? And ln of x to the n, this right here, equals n times x to n times ln of x, and that's what I'm going to use right here. So my right hand side is going to be ln of 1, which is 0, and the left hand side is going to be simply ln of e to the x. So this is going to be simply x. So my solution is x equal to 0 when u is equal to 1, right? Now let's take a look at the second possibility, that is u is equal to 7. when we work with that, I'm going to use the same, taking natural logarithms on both sides, Tennessee lobsters. When I do that, before I do that, let me rewrite the equation. If I rewrite the equation, resubstitute, I have EU, which is e to the x, equals 7. If I do the ln of e to the x on both sides, ln on both sides, I have ln of e to the x on my left hand side and ln of 7 on my right hand side, and the left hand side turns out to be simply x due to the logarithmic properties, and the right hand side is simply ln of 7. There is nothing much you can do on this one, so the solution for this is x equals ln of 7. So we have two solutions, and those two solutions are x equals 0 and x equals 7. In general, it's a good idea to plug it back in to see if they are check your answers. In this case, you know, go home and check your answers afterwards and see if that satisfies, or not. All right, I will stop it right here. In the next video, I will talk about solving logarithmic equations, right? How do you solve the logarithmic equation and so on. I'll talk about it in the next video. I'll stop it. This is the part 1, so we'll do the part 2 later. I'll see you in a bit.